In the rest of this presentation, we're going to be considering four issues. First of all, architectural trends, how we got where we are today. Second, types of parallelism that are available in multiprocessors. Third, the Flynn taxonomy, which has served for a half a century to identify the different kinds of parallel architectures. And finally, the scope of topics we'll be covering in this class. More and more components can be integrated on a single chip. We know that from Moore's law, which is famous for saying that the number of transistors on a chip will double every 18 months. That means that more and more components can be placed on a single chip. Now I want you to pause at this point and look up on the web how the number of components per chip, the number of transistors per chip, has changed in recent years. I'd say especially since 2016 when the textbook was published. Unlike the other classes, in this first class today, we're going to be using Google Forms for in-class exercises. After today, they will be quizzes within the videos. But for today, you get attendance credit by filling out the Google Forms. So you can look at the course schedule page on the web, and that will give you a copy of the slides. You can also look at the course schedule page, and there are a set of links below Lecture 1. The first link will take you to the first exercise for the day, and you can click on that, pull up the Google form, browse the web, and answer it. So after you finish doing that, then we can resume the video. Well, until recently, performance increased just as fast as the number of components on a chip, as the clock rate would continue to rise proportional to the number of transistors. Two architectural techniques supported this. First of all, caches, which were an active area of research in the 1970s and 1980s. They started as a single-level off-chip SRAM cache, then the cache moved on chip, then more levels of caching were added, to the point where today it's not uncommon to have a processor that has 3 levels of cache, some of which may be shared between different cores on a chip. And the second issue that helped was instruction level parallelism, where different instructions or parts of different instructions could be being executed at the same time. So that allowed you to begin one instruction before the previous instruction was completed. And if the previous instruction took a long time, let's say it was a division, or even more importantly, it accessed memory, you could get a lot of parallelism in that way. Performance gains from uniprocessor systems were high enough that most multiprocessor systems simply weren't viable. When an application got too slow to run on your current computer, you just went out and got a new one. And because that was essentially a uniprocessor application running on a computer that was either a uniprocessor or looked to your application like it was a uniprocessor, you could take old code and run it on new computers. You didn't have to do any adaptation, so there was no real incentive to move to a multiprocessor. Well, consider a 100 processor system with perfect speedup. So if you had perfect speedup in an application, and it is a rare application that can give you that kind of speedup, but if you did, it would be 100 times faster in year 1. It would be 62.5 times faster in year 2, and by the time you got to year 10, it would be slower than a new single processor system. So it's pretty clear that the performance advantage of multiprocessors went out of effect pretty quickly in those days. Single processor performance caught up in just a few years. But that wasn't all of it, because it takes longer to develop a multiprocessor system than it takes to develop a single processor system. So you have more startup overhead, more investment that you need to put in before you get the first unit out. And secondly, because the system is more expensive, you don't sell as many of them as you sell of single processors. So low volume means that your cost per unit is higher. And then because the cost per unit is higher, people really think about whether they want to buy one, and they don't buy them so quickly either. And then finally, perfect speedup is unattainable. Well, there are a few applications called embarrassingly parallel that can come pretty close to perfect speedup, but no application can actually get there, and most applications are well short of perfect speedup. So a multiprocessor doesn't get you n times as much processing cycles as n uniprocessors do. Well, back in those days, how did uniprocessor performance grow so fast? Two trends have played a role. First of all, smaller transistors and architectural and secondly, architectural innovation. The two architectural factors were, first of all, that risks came into prominence in the early 1980s. The 1970s were a time of complicated computer architectures when it was considered that programming was more expensive than creating the architecture. So to lower the programming overhead, you should make the architecture do more of what programs wanted it to do. So you had some really complicated instructions, including procedure call instructions that moved a lot of registers and pointers around all in a single instruction just to make it easier for the compiler to generate code. Well, that really didn't make a whole lot of sense because you weren't simplifying programming. You were just simplifying the task of writing the compiler, and the compiler is written once and compiles lots of programs, so the advantage was not what it seemed to be. So at that point, it became clear that, we really want to use a simple instruction set, yet we want to make it compatible with old instruction sets. So that means that the CISC instruction set was actually re-implemented with RISC instructions behind the scenes. So every CISC instruction would be translated to one or more RISC instructions behind the scenes, and then you'd get your simple architecture in the back end, where your front end act as if it was a complicated architecture, so it could run old code. Also, superscalars came in. That means that in the architecture, two or more unrelated instructions could be started at the same time. Not just overlapped, but actually started at the same time. But see, the key in this was unrelated. If one instruction computed an input that was needed by the next instruction, in other words, an operand needed by the next instruction, that first instruction had to finish, or maybe not quite finish and write the value to a register, but it had to get pretty well finished before the next instruction could start. And so that meant that the concurrency that was available was limited. And because of the fact that instructions, some of them finish faster than others, that led to out-of-order execution, where you could start and even finish a second instruction before your first instruction was finished. Your instructions could finish out of order, but all of the results that they computed had to be kept kind of behind the scenes in the computer architecture so they could be written to registers in memory in the proper order, in program order. And that technique was actually achieved back in the early 1960s with Tomasulo's algorithm. And if you've taken ECE 563, I know you've studied that. Okay, and then in addition to instruction level parallelism, there's memory hierarchy, where caches were developed to exploit spatial and temporal locality. Now, if I were in a face-to-face class, I'd ask you what you thought of the spatial and temporal locality were, but since we're not in a live class now, I just suggest that if you don't know, you look up reference locality in Wikipedia, and it'll tell you everything you need to know. And then, of course, there are multiple cache levels. So if a value, if a data item is not cached in the first level cache, you can look in the second level cache or maybe even the third level cache before you have to fetch it from main memory. Well, uniprocessor performance growth has stalled. A source had been instruction level parallelism, but instruction level parallelism ran into, first of all, the memory wall about the year 2000. It became clear that memory speeds were not increasing at anything like the speeds that processor speeds were increasing at. And that meant that if a processor instruction didn't find the data it needed in the register or in the cache, and it had to go to memory, that was like hitting a wall. It would shut it down for maybe up to 100 instruction cycles before the data item could be retrieved all the way from main memory if it missed in all the caches. And that was a really big performance hit. And so that meant that you couldn't get the same kind of improvement that you did up until about 2000. The second wall, which was actually hit just a few years later, was the ILP wall. You started off with dual issue superscalars, then you went to quadratic issue superscalars, and after that you really didn't get much performance improvement, but you did get quadratically increasing complexity. Remember what I said about two unrelated instructions being able to be started at the same time? Well, if the instructions, in order to determine if the instructions are unrelated, you've got to be able to compare the operands of each one with the results of the other one. And as you get more instructions that you're starting that you're trying to start at the same time, you've got to make more comparisons. If you're trying to start 4 instructions at the same time, you've got to compare the operands and results of of each of the 4 of them with all the other 3. So the complexity increases rapidly, and that means that we don't have the performance improvement that we used to. And there's another issue too, and that's power efficiency. U.S. data centers use 90 billion kilowatt hours of electricity a year, and that's the amount that would be generated by 34 large coal-fired plants. And you know, they're just not building those anymore, and so it's not really possible to get the power that we need if we were going to go with complicated processors. Simple processors are much more effective. And so in the next video, we'll look at the various kinds of parallelism that you can get with simpler processors.